So today we have Julia Handl, from professor at University of Manchester at Alliance Manchester Business School, and also she's a fellow at UK Alan Turing Institute. She's done a lot of research in optimization, machine learning, operational research, with many applications in medicine, different engineering-based problems. Also, first time I find out the work of Julia was reading some of her paper on using multi-objective for semi-supervised learning, semi-supervised clustering. So, and something similar but a bit different, multi-objective optimization on unsupervised learning she's going to talk about today. So over to you, Julia, and you're listening to your presentation.
Thanks, Hadi. I'm going to try and share my slides, but that's the thing I usually forget, so that would be a good start. All right, can you see those?
Yes.
Yeah. Okay. Great. Thank you. Thank you very much, Kate and Hadi, for the introduction, and thank you so much for having me this morning or late afternoon in Melbourne. So it's always tricky to select a topic to talk about on these occasions. After some discussion with Hadi, I decided I would talk about some of my work on using techniques for multi-objective optimization in machine learning, and specifically on that part of my work that's focused on the use in unsupervised learning problems. Interestingly, that's an area of research that I started to work on during my PhD. So some of the work I'm going to talk about spans back to 2006, 2007. But then the presentation actually also gives me a chance to talk about some very recent work that we've only just submitted this month. So in terms of the structure of my talk, I'm just going to start with very briefly and at quite a high level introducing the ideas of machine learning and multi-objective optimization, which are really the two key areas that this talk touches upon, and to discuss the rationale for integrating those two techniques in some settings. And then in the second part of the talk, I really want to just briefly highlight three different applications of multi-objective optimization in quite closely related unsupervised learning problems. Okay, so starting with machine learning. So at a generic level, machine learning is really about drawing inferences from patterns in data. And two core classes that we often differentiate between are supervised learning and unsupervised learning problems. There's also reinforcement learning problems, but I won't talk about those today. So let's focus on supervised learning versus unsupervised learning, how these are similar and how they're different from each other. So in supervised learning problems, really, the thing that differentiates them from unsupervised learning is typically some information about what it is we're actually trying to predict and availability of information about that outcome for at least some of our training samples. And so that outcome of interest could be a class membership. So it could be information like for a particular customer, whether that customer purchased or didn't purchase a particular product. So it could be a binary class membership, or it could be something more complex. It could be an integer, or it could be a continuous outcome. For example, the amount of sales generated by a particular customer. But the important thing here is that there is a specific target variable Y that we really know that we're interested in trying to predict about future samples in our data. And then supervised learning is really about trying to identify and use other features, other information we might have about the same customers, the same data points, in order to predict that outcome. So at mathematical level, it's really just a matter of building a model that maps from our feature or attribute space X to that target outcome space Y. And these models obviously can be of varying complexity. So those could be very simple regression models, and at the other end of the spectrum, they could be deep learning models. So models that are highly nonlinear, highly complex in making that mapping. So unsupervised learning, let me just move on with this. So unsupervised learning really is just different in the sense that we don't have that explicit information about what it is we're trying to learn. So we can think of simply having the same kind of data, but what's missing on this occasion is explicit information about the target outcome of interest. So we still have that feature space X potentially, but we lack information about the target outcome, why we're interested in. And so unsupervised learning problems are much more about exploring that initial feature space X in order to understand relationships in that data, to potentially identify homogeneous groups of data points within that space, etc. So that's really the fundamental difference. It informs the kind of approaches that we can use in addressing an unsupervised learning task. Yeah, so these days I have quite a few applications that look at marketing settings and say, for example, in marketing, a very typical example of an unsupervised problem would be a customer segmentation. So we start to look at the data set. We want to understand what the core groups of customers are in our data set, but we don't necessarily know beforehand how many groups there are and what it is, what kind of groups we're really interested in. So one thing to highlight here, because we're going to use that later, is the fact that quite often in unsupervised learning settings, our feature space X may not actually be directly available. So there's quite a few applications of unsupervised learning where what we're actually working with is just relational information. So if we have a feature space X where we can describe each data point as a vector, it's always possible, of course, to use dissimilarity functions to derive a full dissimilarity matrix describing relations from that. But we can also use a lot of unsupervised learning approaches if all we ever have access to is that dissimilarity information alone. So I'm not necessarily going to make an assumption here that we have the access to feature information. Dissimilarity information between data entities is often sufficient. And I'll talk about some approaches that specifically cater for those settings. So the second key concept we're going to use today is multi-objective optimization. And so multi-objective optimization problems arise in any context where we're trying to optimize something, but it's very difficult to identify a single criterion or a single objective that we want to maximize. Yeah, there's a lot of practical context in which often actually there's multiple objectives we want to achieve. So for example, if we want to design a product, we typically have a number of desirable outcomes related to that. For example, we may want it to be both effective and cheap. And it's not difficult to see that quite often these different outcomes won't be aligned, and there will be some level of conflict between them. And it's those are kind of problems where we expect conflict between the different criteria where multi-objective optimization techniques are really come into play. So mathematically, what a multi-objective optimization problem really leaves us with is a situation in which we're trying to identify solutions to a problem. So I'm representing those here as my X. So X is just a vector representation of a possible solution to my problem in that is made up by a number of decision variables. And if I'm treating this as a multi-objective optimization problem, it means I'm using a set. Rather than using a single objective function, I'm using a set of objective functions. So I've numbered these 1 to m here. And in terms of thinking about this problem, what I really have is a mapping from my decision space X describing solutions to the problem to a multidimensional objective space F. So for each of these potential solutions to the problem, I actually have a vector of its objective values that positions it in that objective space. Now, the complication of these kind of problems is that usually we are no longer able to identify a single optimal solution to that problem. So as I just said before, it's quite unlikely that the product that is the cheapest will also be the most effective. There's likely to be some trade-off between these two objectives. And so more generally in these multi-objective optimization problems, we can no longer impose a complete ordering between our solutions, but the best we can do is to impose a partial ordering. So there will be some solutions in that space where we can definitely say that they're better than others, but equally, there exist pairs of solutions which are incomparable. And so specifically, for example, in this figure on the bottom right, if you focus on the two white dots on the right-hand side, you can see that so this assumes a maximization problem here. So we have two objectives that we're trying to maximize. And those two solutions highlighted as white circles are incomparable in the sense that one of them performs better on objective set L, but worse on objective set M, and is the other way around for the other one. So each of them is the best performer on one of the objectives, but it's outperformed on the other. And therefore, without additional information, without additional preference indications from a decision maker, we cannot differentiate between these. And we're potentially interested in generating and exploring both of those solutions. So what that leads us to is the recognition that in a multi-objective optimization, what we typically have is a set of Pareto optimal solutions. So rather than a single solution that's optimal with regards to all of our objectives, we can identify a set of solutions that represent the optimal trade-offs for that particular problem. And it can be very useful to identify those because it allows us to get a better understanding of the conflict between our criteria, and it allows us to potentially inform decision makers much better and help them understand what those trade-offs are and help them navigate through that set of trade-off solutions in order to really find their preferred solutions. So there's a range of techniques available to address these kind of multi-objective optimization problems and to try and generate, identify the Pareto optimal set or close approximations to it. And the main technique that I've used in my research are evolutionary algorithms, which are very popular because of the fact that they're population-based, and so they're able to try and find an approximation to this optimal set in a single run. But that's not by no means the only choice, and a lot of the work that I've done while it's used evolutionary algorithms, it could very easily be adopted to use other types of meta-heuristics. Okay, so why integrate these two concepts? So what are the touching points between multi-objective optimization and machine learning? Well, if you spend a little bit of time working with machine learning techniques, I don't think it's difficult to recognize that actually in the vast majority of machine learning problems, we are dealing with multiple objectives, multiple criteria. They're just not always explicitly considered during model construction. And this applies really to both supervised and unsupervised learning contexts. And I've just highlighted some of the really well-known trade-offs on this slide here. So, for example, the second of these on my slide here, the need for explainability versus the accuracy of model predictions, that's something that's very widely discussed at the moment because that's one of the areas where deep learning obviously is making a lot of inroads in terms of the accuracy of models, but it comes at that cost of explainability. And realistically, in a lot of applications, the decision makers might have very clear expectations in terms of how transparent, how explainable models are. And quite often that leads to tough decisions around plausible model choices. And similarly, another trade-off that's very commonly discussed and well known in the machine learning literature is obviously bias variance trade-off. So the general trade-off around the complexity of our models versus the risk of overfitting. There's also more pragmatic trade-offs. So the third one I've highlighted here, so there may be practical considerations related to, for example, implementation or disruption costs within the domain. So there may be additional criteria on models that come from the domain context. And there may, for example, be criteria that influence the way in which we assess misclassification costs. Yeah, so at a generic level, sort of the most standard machine learning techniques assume that every misclassification is as bad as any other. But again, there's obviously a lot of applications where that isn't correct. And for example, the medical domain is an example of that, where we all know that the mistakes made by diagnostic tests, false positives and false negatives, might potentially have very different implications in terms of what they mean for patient safety. And so there's a trade-off, and there are potential attempts made to balance those. Yeah, so this isn't really a new idea that multiple criteria are relevant in machine learning. It's really something that, if you look at the literature in machine learning, it's always been ingrained in terms of a lot of the methodologies. What hasn't been considered as much is how we could actually try and integrate some of these additional criteria much earlier during model construction. So typically, a lot of the way in which these considerations about multiple criteria are integrated are either in how we select the models we work with in the first place, or afterwards at the model selection stage of the work. And so what I've been hoping to try and do with multi-objective optimization techniques is to bring some of that forward into that generation of candidate model stage. So by making explicit the multi-criteria nature of some of these problems, when we're actually building the models, we would hope to really identify solutions that reflect optimal trade-offs between those criteria, rather than integrating that as a late secondary step. So that's the idea in this work, really, that we're moving from that model selection stage forward to the generation of candidate models step, and think about using more comprehensive formulations of the problem at that point in the model building pipeline. Yeah, and so there's a recognition here that obviously machine learning is very heavily underpinned by optimization. The majority of models use optimization somewhere, but typically that optimization step is formulated as a single objective optimization step. Sometimes that objective might reflect a trade-off between two different criteria, but in that case, it will be weighted. So it will essentially be several criteria that have already been collapsed into a single objective through, for example, a weighted sum aggregation. If we move from that kind of approach to an approach that uses multi-objective Pareto optimization techniques, so that actually explores the set of optimal trade-off solutions, that has the advantages of a more comprehensive problem formulation. It allows us to delay decisions about preferences until we actually understand the problem better. And it potentially allows us actually to effectively identify a number of promising solutions that we could then utilize at later stages of a model building pipeline. So it can also be quite useful as a kind of filter to just retain a number of possible candidates for further analysis. So there's three different unsupervised learning problems that I wanted to briefly talk about today. And these are quite closely related, but they have their differences. So the first one I'm going to start with is cluster analysis. So cluster analysis is really just about identifying natural groups within that feature space X. So identifying groups of data points that are similar and trying to differentiate them from other groups that are quite different. We're then going to look at how the problem of cluster analysis, how that actually can be considered in a multi-view context. So multi-view learning looks at machine learning problems in which we have multiple different feature or dissimilarity spaces in which our entities are described. And so we're moving from just clustering problem to a problem where we're trying to identify groups that are homogeneous with respect to a number of different feature spaces. And then finally, I'd like to look at community detection, which is essentially clustering on graphs. Yeah, so it's a very closely related problem, and there's actually a lot of similarities in the approaches I've used in those two problems, but there's some particularities that make it different from clustering as well. And the work I've done in that area actually looks at a particular type of graph, which are bipartite graphs, and I'll talk a bit more about what that means in a moment. So let's start with clustering. So I've got an example of a very simple data set here. So this is an example of a data set where our feature space, our attributes is just two-dimensional. So we have an X and a Y feature, which means we can easily visualize this data set in the form of a scatter plot. And so if you look at this scatter plot, I think that most of you will probably agree with me that in this particular data set, we have 11 clusters. And if you disagree, then I've probably miscounted, but I think we can generally probably be in agreement about the number of groups we can see in this data set. And that's, of course, because the data set is two-dimensional. Yeah, so in 2 dimensions, humans are really not beatable by computers in terms of our ability to recognize patterns in that data set. So the idea in cluster analysis is not to work on 2-dimensional data sets and get a human to be beaten by a computer. That would be an unnecessary thing to do, because actually visualization is still one of our most effective ways of bringing analysts into machine learning, because we're so good at pattern recognition in 2 and 3 dimensions. The reason why we often use 2-dimensional benchmarks in cluster analysis is because it allows us to understand what our algorithms are doing. And the hope behind the design of better algorithms that work well in 2 dimensions is, of course, that they can generalize the idea of clustering to much higher dimensional spaces where humans start to be ineffective. Yeah, so in 2D, humans hard to beat, but in 30D, we would hope that a clustering algorithm can do a task that humans would intuitively find very difficult. But yeah, so on this data set, I'm using colors here to show a clustering of this particular data set, and I think there's not really a lot of a disagreement probably around this particular partitioning. So why talk about multi-criterion clustering? So when we look at the literature on cluster analysis, one of the first things that's striking is that there's a very large number of different clustering algorithms and clustering criteria available that we can use to address that problem. And the reason for that is the fact that clustering as a task is really not very well defined. So there's a sort of loose definition of clustering being around finding homogeneous groups and finding groups that are well separated from each other. But mathematically, there's a lot of possible ways in which we could express this. And what that leads to is when we look at individual clustering algorithms, we can see that even for very simple data sets, clustering algorithms might return very different results based on these specific mathematical assumptions that go into the formulation of the algorithm, that go into the formulation of the clustering criterion used. So this animation here is a really simple example on a projection of the iris data set. So on the top left, you've got the correct cluster assignment for this particular data set. So we have 3 clusters. And then on the top right, we've got the results produced by the k-means algorithm. If we increase the number of clusters from 1 to 5, at the bottom left, we've got the single link agglomerative clustering algorithm. And on the bottom right, we have a model-based clustering algorithm. And so the takeaway really from this animation is that even for this very simple data set, and even for these very established clustering algorithms, which are some of the most commonly used types of approaches, we get quite different results. So they're very inconsistent in terms of the clustering solution they actually produce, which, if you first start to work with clustering algorithms, can be really confusing. Yeah, because not just, so algorithms like k-means actually give you slightly different results every time you run them, but on top of that, you might get very different results based on the algorithm you use. So there's a really important appreciation there that actually by selecting a particular clustering algorithm for a task, we're already making quite significant assumptions about the types of clusters we will be able to identify. So our work on multi-objective clustering has really tried to, well, I wouldn't actually say fully address that. It has started to try and think about that by acknowledging, explicitly acknowledging the fact that there are multiple criteria, multiple objectives that tend to be relevant in cluster analysis, and that actually maybe we should be able to do better if we at least incorporated some of those into the generation of clustering solutions. So what we've got here on this slide is just an illustration of the idea behind that. So in this case, we say, okay, if we want to formulate clustering more comprehensively, let's maybe use different objectives. So I've got one objective that captures compactness of clusters on the y-axis here, and a second objective that captures how densely connected clusters are locally on the x-axis. And what a multi-objective algorithm that should then be able to give us is a set of optimal trade-offs between these two criteria. And as you can see with those three solutions I've highlighted here, those will correspond and capture some of these quite different possible segmentations of the same data set. Yeah, and somewhere within that set, we hope we'll be able to identify the solution that best fits the human expectation on that data set. But where exactly that solution sits, we may expect that to shift around. Yeah, it may sometimes be in the center of the front, but it might sometimes be on the extreme ends of this trade-off front, dependent on the particular properties of our data set. So the work that I started doing my PhD actually looked at producing a multi-objective evolutionary algorithm to do exactly this. So to try and identify the optimal set of trade-offs for a particular set of clustering criteria. And it's not actually that straightforward, primarily because of the fact that clustering problems typically involve thousands, at least, of data points. And that makes the search space grow very quickly for evolutionary algorithms. So the key challenge really in addressing this as a multi-objective task is finding representations that allow the evolutionary algorithms to scale to those kind of problems. But once we have a good representation, yeah, we should really be able to explore those trade-offs. And what we should find as a result, and I'm showing that here with some solutions from actual algorithms, is that by using several objectives, we genuinely focus on the trade-offs, and we should find that some of the algorithms that focus on a single criterion primarily generate solutions that are actually dominated. Yeah, so we looked at a objective space before where we were looking at a maximization problem. So in this case here, we have two objectives that we're trying to minimize. So ideally, our best solutions are the ones that lie in the bottom left here. What you can see in red is the approximation front that a multi-objective clustering algorithm has found in this case. And then you can see that, for example, in pink, we've got the various solutions produced by the k-means algorithm, or in blue, we have the various solutions produced by the single link algorithm. And you can see that the large majority of those solutions become dominated. So they're actually not optimal trade-offs between these two criteria, which we should expect because these algorithms aren't aware of those additional criteria. But it just shows that it genuinely makes a difference to bring those criteria into the problem formulation. So we potentially generate better solutions, but then also once we've generated those solutions, we can actually analyze the shape and the content of these priority optimal sets that we obtain and potentially use that to derive additional information for additional insight into a problem. The other thing is that in cluster analysis, there is an argument that model selection in cluster analysis is generally a lot less straightforward than in supervised learning because we lack a very clear indication of what performance actually means. And so there is an argument that the success of any clustering algorithm is best assessed at the very end of a modeling pipeline. So for example, if we use clustering as a pre-processing step to a further forecasting or supervised learning step, then the best way of assessing the success of the clustering solution is by actually feeding back the output and the performance of that final supervised learning step. And so if we look at clustering in that way, then it makes sense to use the generation of clustering solutions simply as a step of generating a number of solutions that are promising in terms of their trade-offs between criteria, but reserving final model selection until we actually have that feedback from subsequent modeling steps. Whoops. Oh, yeah, no, that's where I want to be. So in terms of the implementation of this, so I implemented the first version of that during my PhD. That algorithm was called mock. And then a few years back, we actually looked at improving the scalability of that algorithm further, resulting in a method called delta mock, which essentially allowed us to change the level of resolution that we're looking at in a problem in order to help with scalability to larger data sets. But one key thing I wanted to highlight on this slide is that this, I mentioned earlier that the representation of a clustering solution is really, it is not straightforward in clustering. Yeah, so one common way of trying to reduce the size of the search space that we're dealing with is to use a centroid-based encoding, so to represent a solution, a clustering solution within an evolutionary algorithm by simply using prototypes of each cluster. Yeah, so the advantage of that is that the problem representation grows with the dimensionality of the data set, and it grows with the number of clusters that we're looking for, but it's not directly linked to the number of data points in a data set. And so that's one of the reasons why representations based on prototypes have been quite commonly used in developing evolutionary algorithms for clustering. The limitation of the approach is that a prototype-based encoding implicitly makes a direct assumption about cluster shapes. So prototype-based encodings are well known to be biased towards spherical clusters. And that's not optimal if we are actually striving to develop a multi-objective algorithm, because if we have two criteria, one of them is compactness based, one of it relates to something else, then by choosing a prototype-based encoding, we're directly biasing our algorithm towards clusters that align with that first objective. So in my work, I've tried to use a more flexible representation, which is graph-based, with the idea of avoiding that introduction of a bias at the representation stage already. And what you can see in that top plot here is a comparison of a number of different ways of representing clustering solutions in evolutionary algorithms. And we're evaluating the performance of the approaches using a measure called ARI, that's the adjusted random index. It compares to the goal truth, to the known correct clustering solution in this case. So one is recovery of the optimal, the correct solution. And if you focus on the purple stars here in the purple line, that shows you how well an evolutionary algorithm with a prototype-based encoding does on this problem. And the three lines above that, so the red one, the green one, and the yellow ones, are different versions of our representation. And so you can see that there's a big performance gap that arises not from the choice of objective functions, because we've used the same objective functions here, but just from that additional consideration of how we actually represent a clustering solution. Now, the representation, yeah, I said, it's essentially graph-based. It tries to transform the problem of cluster analysis into evolving graphs that represent the structure within the data set. And essentially, yeah, we're evolving those graphs, and within those graphs, we're interpreting connected components within the graph as individual clusters. Yeah, so that's at a high level how that encoding works. And then the work on delta mock essentially looked at ways we can reduce the search space by identifying parts of that graph that we know are not interesting to change during the search, and that we can essentially maintain as individual blocks, collapse them into specific bigger components. Okay, so let me just move on from that to a slightly different clustering problem, which is the problem of multi-view learning. And so this arises in domains quite often where it's difficult to actually characterize dissimilarities or similarities between the entities we're trying to cluster. And so in my own research, for example, an example of that arises in protein structure prediction. There are clustering steps involved in prediction pipelines for protein structure prediction, but one of the difficulties is in actually assessing how similar two structures are. And there's a variety of different tools we can use to do that, all with their own disadvantages and advantages. So one way of thinking about this problem is that what we're left with is essentially a multi-view clustering problem. So we have a set of entities, and once we try and compare those using a similarity or dissimilarity function, we are left with a number of distinct dissimilarity matrices that all give us a slightly different picture of our data set. So when we then proceed to clustering, our clustering algorithm should try and look at these different views and integrate them and find clustering solutions that are supported across all of these views. So and doing that in a multi-objective optimization spirit, so using genuine Pareto optimization, should be advantageous in settings where we have views that are of different reliability. Yeah, so if all of our views are equally good, if they're all equally important, then multi-objective optimization may not add much, because we would expect the best solutions to this problem to be those that correspond to that lie in the middle of the Pareto fund, and that, you know, sort of really do well across all objectives. But as we vary the reliability of the individual objectives, we may actually find that our best locations are biased towards one or the other of the views. And on this slide, you can just see an experiment that looks at that. It varies the reliability of different views by artificially adding noise to those views. And then we can see how the optimal solution, which is shown as a red dot here, how that moves around in the approximation front. So on the top left here, we have a problem where there's no noise in either of our views, and you can see that the optimal solution is somewhere in the middle of the front. But as we add noise to either the right views, that's on the right-hand side here, or to the other view on the bottom left here, you can see that that red dot moves around the front. Now, so we can see that if we have different reliability of views, multi-objective optimization could potentially be useful. But there's a challenge there in terms of how we can get existing multi-objective clustering algorithms to actually extend to that setting. Because one of the limitations of the representations, both in prototype-based encodings and in the encoding that I've used in my previous work, is that the representation itself is rooted in one of the original dissimilarity spaces. So by simply using those representations, we again are left with a problem where optimization is immediately biased towards one of these criteria, just based on the fact how we've decided to represent clustering solutions. And so this is what some of my recent work has looked at, to try and overcome that challenge and move towards multi-objective algorithms that can effectively work not just with different clustering criteria, but they can work with criteria that quantify the success of a partition with regards to different dissimilarity of feature spaces. So one of these pieces of work has looked at our own graph-based representation and how we can extend that, how we can make it more general so that it can construct the initial representation based on information that draws on all of the available views or dissimilarity spaces. And I'm not going to go into detail on that today. I'm happy to do so during questions, but I'm just trying to keep an eye on time. And the other approach that the other work that we've done looked at adopting a prototype-based encoding, but again for the same setting, so that we can solve clustering problems in which we have multiple views, and more importantly, actually do that in settings where we have many views. So by many view optimization, we often mean multi-objective problems in which we have 4 or more objective functions, where we need to start using particular types of algorithms to still be able to efficiently approximate the Pareto optimal set. So these are 2 different algorithms. So one of this delta MB is the extension of delta mock. It's under submission at the moment. And the other one is our algorithm MBMC, and that was published last year in Applied Soft Computing. But essentially in that work, MBMC, we're using the fact that the main approach to solving many objective problems is to use algorithms that use scalarization approach during the search. They use reference vectors. And in that paper, we actually show that by having the direct access to those reference vectors, we can avoid the biases that prototype-based encodings typically have towards the particular feature space that the prototypes are encoded in. Okay, so let me just move on very briefly to the last application I wanted to talk about, which is community detection in bipartite networks. So this is something we looked at because of a project with a company in the UK where we were looking at the UK procurement network. And they were essentially interested in deriving a kind of recommender system. So within the procurement network, essentially we have public sector organizations, our buyers. They invite competing offers from suppliers. And so what they're interested in is identifying suppliers that may be interested and that should be made aware of new opportunities. Yeah, so we can think of this as a graph in which we have these three different types of nodes. So we have the buyers, particular contract opportunities that become available are in the form of notices shown with the diamond shape. And then we have the suppliers that have actually been successful in being awarded a particular contract. So the problem is difficult because we have only very partial understanding of the system because we can only observe the successful tenders. So we can only observe edges between notices and suppliers when that supplier has actually been successful in obtaining that contract. What we don't have is information about which notices were actually of relevance to particular suppliers and which ones they bid for and were unsuccessful to get. But ultimately, that's where the company wants to move. So they want to recommend a system that would highlight potential links between notices coming from a particular buyer and suppliers. It's difficult to formulate as a supervised learning problem because of the difficulty of obtaining negative training examples in this case. So we looked at this using an unsupervised approach. Okay, so, and one of the things to recognize about this problem is that if we're just focusing on suppliers and buyers, then essentially we're left with a problem that can be conceptually shown as a bipartite graph. So a bipartite graph is a graph structure in which we have two different types of nodes, and edges can only ever be between those two different types of nodes. Yeah, so here we can have an edge between a buyer and a supplier because that supplier has engaged and been awarded the contract from that particular buyer, but we wouldn't ever observe edges between buyers and we would never observe edges between different suppliers. Yeah, so the edges are strictly between nodes of a different kind. So that's a bipartite graph. And one common way to studying bipartite graph is to actually look at them in the projections into either of the two modes. So we can look at this bipartite network at the top here, by either projecting it into the space of just the buyers or by projecting it into the space of just the suppliers. And we would draw an edge between buyers or we would draw an edge between suppliers only if they share a neighbor in the original graph structure. The advantage of that kind of projection is that we're back with a more ordinary graph structure. So it's more straightforward to apply existing tools from community detection from graph analysis. The other argument that has been made is that it's a more natural way of looking at those structures because it's better define what a community actually means if we're looking at that graph in these projected spaces. So in our work, we actually wanted to use an evolutionary algorithm to actually compare these different formulations. So how effective is community detection if we do it in the original bipartite graph as compared to doing it in the projections? And the great thing about multi-objective optimization is that it makes, once we have the working algorithm, it's very easy to then just replace different objective functions and to evaluate the community structure either in the original graph or in those individual projections. So we developed the evolutionary algorithm framework that allows us to do that. Quite a lot of work went into refining aspects of the representation and of the mutation probabilities to try and make this more scalable by biasing the search towards those edges in the graph that we really thought were important. And yeah, so there are a lot of heuristic bias integrated through how we designed initialization and mutation operators for the search. And the findings are quite interesting, because some of our findings, so I know this is probably too small for you to see, so I'm just going to highlight two of those box plots here on the left-hand side. So again, this looks at recovery of the ground truths on some instances, and we're comparing against some very standard techniques from community detection, and also some approaches specialized for bipartite graph structures. It's the adjusted random index again, so higher values are better. We want to be as close to one as possible. And what you have on the right-hand side in pink, red, and orange are three different evolutionary algorithm formulations of this problem, where mean partite 3 is the algorithm that works on the projections rather than on the original graph. Yeah, mean partite 2 just works on the original bipartite graph structure. And so interestingly, our research actually confirms what's previously been discussed in the literature, which is a better ability to consistently retrieve the correct community structure if we are focusing on the projections and integrating the view across the two projections rather than working on the original bipartite structure alone. So that's really one of the core takeaways from that finding. This is under submission, but there's also quite a bit of ongoing work there in terms of further improving this approach. Now, let me just very quickly wrap up, because I know I've already gone on for too long. So some takeaways from this research, or the way I see them. So I think that some of this work's been useful just in making very explicit and debunking the myths that in some of these learning problems we have a single objectively optimal solution, because the reality is that in a lot of machine learning problems we don't, and actually selecting across models can be very difficult, and potentially multi-objective optimization and ideas from multi-criterion decision making can really help in that space. The techniques we've devised, they support data exploration really well in terms of allowing us to really understand those trade-offs between some of those criteria, much more than we were able to do with traditional techniques. And they can potentially be useful as a formal and objective mechanism to help us retain solutions that are genuinely optimal trade-offs, so that we can then exploit and build on those at later stages of the model building pipeline. So that brings me to the end of my talk. I just wanted to thank some of the funding bodies that have made this work possible, and a growing team of individuals who've worked with me over the past few years in advancing this work. Thank you so much for your attention today, and I'm looking forward to some questions.